So today I thought it would be quite useful to just sort of take a look at a side story and discuss aspects or physical aspects of black holes, but also of space-times. So we looked yesterday at quite a formal process, which was the Euclidean quantum gravity type of approach to calculating the gravitational action and deducing thermodynamic properties of black holes. And sometimes when you think about black holes or black hole theorems, you can be fooled into thinking that there's very little going on with black holes in 4 dimensions, that there's like, Schwarzschild, Kerr, Rindler, Kerr, Newman, and that's it. But in fact, there are more exotic solutions with black holes, and one of those I'd just like to discuss today at the end when we come on to acceleration. So I'd like to discuss accelerating black holes. So in fact, we can do more than just have a single isolated black hole, and I think it's quite good to just see that. But first, I wanted to look at rotation in a little bit more detail. So I think Tibra and I have been plotting, as far as your tutorial is concerned, to try and get you to look a little bit at a bit more physical properties of black holes. So in other words, we're going to look at the Kerr black hole. I'm going to discuss the sort of easier bit of it, the bit you can do on a blackboard, and then we're going to leave the trickier bits to you in the tutorial. So let's take a closer look at Kerr. So I'll just write down the metric again. So I've written it down in a slightly different order today. And remember these 2 metric functions. One encodes where the horizon is, and the other encodes the sort of bulging of the black hole due to rotation. So this is the prototypical black hole that we expect to see in nature, because most black holes formed from gravitational collapse will actually have some rotation associated with them. And so clearly, if we're sort of thinking about real black holes, doing actual measurement or observation, this is the analytic metric that we should be looking at. So what we're going to do is to set up the problem to look at geodesics. It's actually, geodesics and Kerr are quite an interesting story, so we're barely going to scratch the surface. What I'm going to do is I'm going to look at geodesics in the equatorial plane, because that simplifies a lot of the problem. Now, obviously, a general geodesic will not be nicely aligned with the black hole. It can sort of pass through the equatorial plane, in which case you see quite interesting effects due to the dragging of frames, the rotation, the dragging due to the rotation of the black hole. So I encourage you to kind of Google it and look at things online. So this is what we're going to do. But just first, let's make use of something that we defined and talked about last week in earlier lectures, and that is the killing vector. So remember, a killing vector represents symmetries of the metric. So if we look along a geodesic, so now I'm thinking, let me take the contraction of the killing vector with the 4 velocity. I suppose that's if it's time-like, but we're dealing with time-like or null geodesics. with the full velocity of our observer, or our particle, then this is just the covariant derivative along the world line of k dot x. But of course, I'm looking at geodesics, so grad x dot of x dot vanishes. So I can pull that out. But then what I'm left with is x dot nu, which is symmetric on mu and nu, and the condition that the Lie derivative of the metric vanishes along the Killing vector k translates into the symmetrized part covariant derivative of the Killing vector vanishes. So if we have a Killing vector, we can construct conserved quantities along our geodesics. So let's look at what that does for Kerr. We've got two obvious Killing vectors in Kerr. The metric does not depend explicitly on time, and it doesn't depend explicitly on phi. So we have a sort of axial symmetry, and we have a time symmetry, although we don't have time reversal symmetry. So that tells us we have a conserved quantity E, which is gt mu x dot mu, because our Killing vector is d by dt. So if I look at what this gives me, that's what I get. So I input my metric, and you now find that, different from Schwarzschild, you've probably seen geodesics in Schwarzschild when you were looking at solar system tests, you've now got the energy, or what you're associating with an energy, also having a contribution of phi dot. So if I look now at theta goes to pi on 2, then what I get is something that looks, sigma just goes to r squared. So the first piece I get is very familiar, looks like Schwarzschild. And then the second piece is dependent on the angular momentum, on the rotation parameter A. So we correct the energy by something dependent on rotation. So for d by d phi, similar story. So once again, I have a mixing what I would normally have called a sort of angular momentum, or an of my geodesic, now also has something that depends on t dot in it. So if I go to theta is pi on 2, so you can see that the angular momentum conserved quantity looks a bit more different. We've got quite a few corrections coming from the rotation. Mm-hmm.
So could we actually interpret these as the energy of the particle and the momentum?
Well, it's usually what the interpretation that we associate with these particular parameters. So as you go off to infinity, you see that the energy parameter does indeed tend to t dot, which would be the energy of a particle out near infinity. And as you go off to infinity here, you can see that by far the dominant contribution is r squared phi dot. So yes, they are these parameters, but of course they're corrected. Mm-hmm.
So what combination of these goes now at the horizon?
Well, so hang on, we're just about to go and discuss. So at the moment I'm just trying to construct conserved quantities for my geodesics. I think you're about to see the answer to this, actually. So. Right, so we've got two conserved quantities. We're restricting theta equals pi by 2, so there's only one thing left, and that is r. Now, although the geodesic equation is formally a second-order equation, usually when we're solving geodesics, we try and write it as a first-order equation, so particle moving in a potential well. And in order to do that, we usually take x dot mu, and we use the fact that our force velocity is either 1 for a massive particle or 0 for a massless particle. Now, the only thing that looks a bit messier here is when I take x dot squared, I'm going to get t dot squared terms, phi dot squared terms, and t dot phi dot terms. So I have to disentangle that combination in terms of these conserved quantities, E and H. So in order to do that, I'm going to define a sort of combined momentum. So this is the thing that you're going to see going null, okay? So I'm going to combine these constants into a sort of transverse momentum in the t phi plane. So here my alpha and beta are just 0 and 1 or 0 and 3, or basically they're the t and phi coordinates. So then p squared, p alpha, p beta, g alpha beta is the combination that we want in our first-order geodesic equation. And so this is what I want. And here I see how to get it. I take the appropriate combination of this sort of little 2 momentum here. And so I get this combination of E and H. So this works out, and I calculate it. I've got this 1 over delta. So that's my p squared piece. So you can see if you were dealing with Schwarzschild, so you just set A equal to 0, you'd end up with this same combination of E over delta, well, ER squared over delta, and here H squared. So our geodesic equation so I said it was a first-order equation. I take the magnitude of x dot squared, and so when I do that, I get this p squared plus the r dot squared term, and I'm going to set that to be equal to eta, where eta is 1 for a massive particle and 0 for a massless particle. So that's just standard computing geodesics. And so I want to rewrite this in a sort of format, up to a factor of 2 at least, as an effective potential. So this, by looking at effective potentials, it often saves you time in terms of, it doesn't give you, without doing the calculation, you don't get the exact geodesic, but it gives you a qualitative understanding of what geodesics are allowed. So it's very useful. And in our case, our effective potential, well, we can just see it from here. It's eta minus p squared times delta over sigma. And so, oops, pulled R's inside, which I shouldn't have. So just by pulling together the expression for p squared, this is what my effective potential is. So you can see the Schwarzschild effective potential hiding in there. And of course, we have an interpretation for each of these terms. So minus 2 gm eta over r, this is our Newtonian term. This is what we would already have in Newtonian gravity, our Newtonian potential. The h squared on r squared piece is a sort of centrifugal repulsion. And so we again would get that in Newtonian gravity. This term here, 2gmh squared over r cubed, this is our standard Schwarzschild GR correction. But I can rewrite this whole bracket here as minus 2gm h minus ae all squared. And so you can see the effect of Kerr. The effect of Kerr in terms of an effective potential is if h and a have the same sign, then that sort of additional gravitational piece is lowered. If they have opposite signs, then it gets bigger. So what does that mean? Well, the way I defined h, if h and a have the same sign, it means the geodesics are co-rotating with the black hole. And so for a co-rotating geodesic, we're saying that this general relativistic correction is slightly lowered by having in the background of a rotating black hole. If you have a counter-rotating geodesic, then it gets a little bit bigger. So it's saying that geodesics around a rotating black hole, they can actually get a little closer in if they're co-rotating. So we'll see that in a moment. So here we have our Kerr bit. So this is the effective potential that you're going to be playing with this afternoon. So what I want to look at a little bit more closely is, again, this is a very simple, I'm trying to do everything on a blackboard, trying to do it analytically, so I'm only going to do tractable problems. But the useful thing about this effective potential is it's equatorial motion, and we find that astrophysical black holes quite often are surrounded by an accretion disk. So in other words, if I sketch what we sort of have, we've got our black hole, and then typically around it so the black hole tends to suck the medium around it, And in a rotating black hole, this will often sort of get itself organized in some co-rotating system. So typically, local matter gets sucked in, and it starts co-rotating with the black hole. Now, approximately speaking, you can model this accretion disk by sort of concentric circular orbits. Now, it's only a model, but it's, something that, again, we can do quite straightforwardly by looking at this effective potential. Now, because we're dealing with real matter and not idealized point particles, clearly this matter is going to interact, it's going to be jostled. This accretion disk can get to be quite an extreme environment, so it gets quite hot. And clearly, as you get radiation, that's a loss of energy. And so gradually, the particles move inwards because of the loss of energy. And then eventually they reach this inside point beyond which there is no stable circular orbit. And so at that point, they get sucked into the black hole. So if let me try and write some of this down. So a circular orbit, if we sort of sketch our effective potential, a circular orbit here occurs when the effective potential has a local minimum. So here we've got, this would be our zero, the way I've defined the effective, but we've sort of, our energy parameter is chosen such that R dot and R double dot vanish at this particular point. So here, that means that V and V primed are 0, but obviously at this point, V double primed is positive, here V double primed is negative, so this is a stable circular orbit, and this one would be an unstable circular orbit. Obviously, it would have a different E value. As you move in over, the parameter H changes and the parameter E changes, and these two turning points move closer together. And so the defining feature of this point here So the defining feature is that it's the limit at which you can have a stable circular orbit. So it's called the innermost stable circular orbit, or ISCO for short. And so this is a sort of quite an important feature of a black hole because it represents the last point at which you've got matter in a sort of stable orbit around the black hole, and it tends to be the hottest point of the accretion disk. And so there's sort of attempts to observe these innermost stable circular orbits by looking at sort of emission, I think it's from ion lines or something, so it's looking at emission from the accretion disks. So it's one way that you can access information about the black hole. So there's there's all sorts of different interesting ways you can try and decode observation of black holes, but this is one of them. And why is it telling you something about the black hole? Well, what we're going to get you to do this afternoon is to look at what the radius of this ISCO is. So what you're going to see is that as you switch on rotation, so the ISCO starts to creep inwards, and so therefore it's going to be at a hotter and hotter temperature, and so that's why you can get some feel for how close the ISCO is to the event horizon, which will tell you something about the rotation parameter of the black holes. Also, if there are any modifications of gravity, they will presumably also tinker with this relation between mass of black hole, rotation parameter of black hole, and innermost stable circular orbit. So again, it provides potential of another way of testing GR in a very strong gravity regime. That's why these things are interesting. So let's have a little bit of a look at what the ISCO is, just to sort of start off the calculation. V and V prime to 0 for a circular orbit. And V double prime goes to 0 for the ISCO. Now, obviously, for the ISCO, we need eta equals 1. We're talking about massive particle orbits. You'll see it's not possible, or we will see in a moment, it's not possible to have one of these with a null geodesic. So just to give you a starting point for this afternoon, so the effective potential, whether you're dealing with Kerr or Schwarzschild, it's sort of constant 1 over r, 1 over r squared, 1 over r cubed. So the fact that the v primed and v double primed are 0 give you 2 quadratic constraints for r. And so the notion is that you can eliminate from these 2 constraints. You can first of all find r, and then you can find h as a function of e or e as a function of h, and then pop it back into v to find out what, to sort of get rid of your final parameter, be it e or h, in terms of a and m. And so that then gives you this radius of the ISCO. So for Schwarzschild, it's quite straightforward. If a is 0, so you can see this top, each of these are going to be 0. So I chose these relations because they give me particularly simple expressions for r. So the top expression tells me that r looks like h minus ae. So if a is 0, that tells me r is plus or minus h. Then the second one is a direct expression for r, and for Schwarzschild, it just tells me that r is h squared over 2gm. So you can see that I can now, without worrying about the value of e just drops out, I can determine what my radius is. So here we've got 3h squared as h to the 4th over 2gm squared. So that gives me h squared. And then once I've got h squared, I can then get r squared. So obviously Schwarzschild's quite straightforward. I don't have to work very hard to get the radius of my innermost stable orbit. For Kerr, you do have to work a bit harder because clearly once A is non-zero, you've actually got E there. You have to use all 3 equations. So just note what you will see So, as I was saying before, if you look at small a, you'll see that if you've got a co-rotating particle, their innermost stable orbit will actually drop. Now let's just, again in the interests of expediency, just look at null orbits. So in this case, I'm taking eta as 0. And I want to look at, I'm sort of really getting at exploring the event horizon here in the sense that we saw yesterday that GTT vanished outside the place where delta vanished. Now I claimed delta was the event horizon. It's easier to see that if GTT formally becomes negative, that you can't stay at rest relative to infinity, because otherwise you'd sort of be traveling backwards in time. But it's not so easy to see that delta equals 0 really is the event horizon. So I'm obviously not going to look at a general null orbit, but I'm just going to give an argument about why that is the case. So first of all, let me simplify as much as possible. If you have a null geodesic, you can always rescale the affine parameter to set equals 1. So there's no, time doesn't move for a null geodesic, so it doesn't really matter what I take my affine parameter to be as long as it's just a constant factor. So V has a somewhat simpler looking form. We don't have the 1 over r piece for a null geodesic. So if I look at a circular orbit, then V primed is 0. So if I look at V primed, I've only got these two terms. So it's giving me a relation between those two terms. So it gives me a value for r. If I take the derivative of this, I get a 3 coming from the r cubed. And I take the derivative of that, and I get a 2 coming from the r squared. So we get a null orbit, just like we do with Schwarzschild, but it's at a rescaled value. And V double primed at this value of r if I look at V double prime, no matter what I do, V double primed is negative. So that means that we can have a circular null orbit, but that it is always unstable.
So you also said V equals to 0 for this, or not?
Yes, but I'm not using that information yet. I can already deduce that my null orbit is unstable if V primed is 0. So for Schwarzschild, A is 0, and you see that R is 3GM, so that's the familiar null orbit for Schwarzschild. And once again, you would just the actual magnitude of V double prime doesn't really matter. What matters is that it's negative. So now I'm going to use the value of V, the fact V is 0, to tell me something about H, and I'm going to take a look at the event horizon of an extremal black hole. Again, I'm doing this particular example because it is analytically more straightforward. So to take the extremal limit of the Kerr black hole, I set the rotation parameter equal to the mass so that the inner and outer zeros of delta coincide. And then for my circular orbit, v equals 0. And now I'm going to see what that implies. So obviously v equals 0, I can rewrite this term here. In this term here turns out to be 3gm over r cubed, h minus a squared. And so I get, remember gm is a, and if I input my value of r, so I've got here, I said that 1 equals gm over r cubed, which is a over r cubed, times h minus a squared. But of course, to get r cubed, I'm going to cube this value, so that's where my 27 comes from. And so I end up with, it's not very readable, I end up with this relation between h and a. So v equals 0 determines the angular momentum constant h. So in this case, h equals 2a is the value of the angular momentum constant that solves the circular orbit equation. So we have that r null, the null radius, is equal to a, which is r plus. So if we put in h as 2a here. So what that means is we've got a circular null orbit lying at exactly the point where delta is 0. Now, if we have a circular null orbit, whether or not it's stable, there is no way that can be inside the event horizon, okay? Because inside the event, once we're inside the event horizon, we are sort of sucked in even further. So this tells us that even though GTT goes to 0, so GTT goes to 0 at, is it 2a? I think it's 2a in this case. So even though the ergosphere is twice as far outside the black hole as the 0 of delta, it's saying that that still is not the event horizon. So this is now giving some justification to the fact that the ergosphere, it does not represent, or, well, I suppose the name tells you it's not the event horizon, but it's justifying the name. So let me just keep h equals 2a and look at what happens as an effective potential. So my effective potential for the null or the massless particle now takes a very simple form. I can factorize it, and if I plot it, looks something like this. Should be exactly on the axis there. And so what you see is that's illustrating the fact that the orbit is unstable. If a photon at r equals a is nudged just a little bit inside r equals a, it will sort of fall down and go down to r equals 0. If it's just nudged just a little bit outside, then it will escape off to infinity. So that picture is justifying the interpretation of r equals a as an event horizon. It's the boundary between photons that will go off to infinity and those that will be captured. So you can see here that if I start off at r equals a, and I'm just pushed just a little bit outside, I will escape off to infinity. So that's supporting the claim I made, which is that R plus is the event horizon. Mm-hmm.
So the external limit is just so that the simple form.
It's just making everything simple. Okay. Yes, I'm trying to keep everything simple. So in this case, obviously, in the extremal limit, r equals a becomes quite special because you'll see that also the ISCO actually goes down to r equals a as well. So it's a very special limit. But if you were wanting to look at away from the extremal limit, then away from the extremal limit, these circular geodesics don't coincide with the event horizon. So you would have to work a little harder to see that indeed a null geodesic just outside the event horizon, or you could escape to infinity, whereas one just inside couldn't. But I'm doing this so I can use the simple argument of circular geodesics and looking at an effective potential in a very simple case. So it's really more just so that everything is, is neat. I think that's probably the. But now you have the tools to actually go and check, right? So I think what makes it more tricky than Schwarzschild is, with Schwarzschild you can see the event horizon by just looking at radial null geodesics, so you never have to worry about angular momentum, but here you don't have that option. That's why it's more messy. Well, you'll see that this afternoon, actually, just looking for the ISCOs. Right. So just to wrap up, I just want to look at another useful physical aspect of observers or black holes in a space-time, and that is acceleration. So we've already kind of seen this, but let me sort of pull it together. So let's imagine we've got an accelerating observer. Then I want to represent that by a world line. Now, usually we spend so much time thinking about solving the geodesic equation in GR, we forget that we actually have non-inertial observers. I mean, we are non-inertial observers on the surface of the Earth. So having an accelerating observer is quite physical, and it's a sort of very, it's almost a default in some sense. But let's look at accelerating observers just in empty space. So I've claimed that we can represent an accelerating observer by hyperbolic sines and cosines. And if I take x dot mu, you can see I've normalized it so that x dot squared is 1. So that's saying that tau is the local time for that observer. So this is what you usually do if you're constructing a world line. Then I ask, what is my acceleration, x double dot mu? And then you'll see that that is in fact a squared times x. Or if I look at the magnitude of x double dot, you'll see the magnitude is a. So this represents, if I sketch it in Minkowski spacetime, here's my observer. And they're moving along a hyperboloid. So this is a uniformly accelerating observer. So let's think about what they can see. So in terms of what this observer can see, the observer can see everything to the past of that light ray, and they can influence everything to the future of this light ray. So you can see that they are, this is like a no-go region. They cannot see it, they cannot influence it. So the uniformly accelerating observer has horizons. There are limits to what they can influence and what they can see. So let's now change coordinates to make this explicit. So I'm going to claim that to change coordinates, I'm going to use the hyperboloids. So I know my observer is sitting on a specific hyperboloid in Minkowski space-time, and so I'm simply going to say, well, let me just take a whole family, let me slice up flat space by families of hyperboloids based around the same origin. So dt squared minus dx squared, which would be my Minkowski distance, now becomes something that looks, certainly it's not trivial, something that looks a bit more complicated. So our observer is at constant rho. So we could zero rho by, say, setting rho primed is rho minus 1 over a. Then our ds squared would just look slightly different, but the reason I did this is I just want to note, compared to the domain wall, where we had sort of 1 minus z over L squared dt squared. So you've got the same feature. So I'm just sort of highlighting that we've seen this before type of thing. So this rewriting of Minkowski spacetime has a name, it's called Rindler. and it represents the space-time of an accelerated observer. So notice that x is always positive, and t, the magnitude of t, is always less than or equal to x. So what we get is, if this is our Minkowski space-time, I'll draw the light rays, then this is our rho equals constant, our hyperboloids, t equals constant, straight lines, and our Rindler wedge is just this quarter of Minkowski space-time. So we sometimes call it a wedge just because it looks a bit like a wedge. So it's a useful little space-time to consider because it's flat, so gravitationally it's trivial, but it has horizons, so it gives you a sort of way of exploring issues about thermodynamics without actually having any matter present. So just to wrap up, I just want to discuss acceleration in black holes. So as I was saying at the beginning, surprisingly in 4 dimensions, even though it looks like, you sometimes hear it said, oh, well, Kerr is the most general black hole. That's true. It's the most general, isolated, asymptotically flat, blah, 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 black hole. It doesn't mean it's the only thing that you can construct in 4 dimensions. And so what I just like to talk about here is something called the C metric. So it's really just to show you what the C metric is and to describe it, and try and just or at least convince you it's something to do with an accelerating black hole. So it has a slightly odd-looking form. And these are just the coordinates that it is usually presented in from a relativist perspective. So it's a metric that has 2 Killing vectors. Like Kerr, we've got a d by dt, a d by d psi. Like Kerr, we've got a metric that depends on 2 coordinates. Here we're labeling them x and y. And so these functions, f and g, are actually polynomial functions. And they're essentially the same function.
What's the last coordinate?
Psi. So the reason I haven't called it phi is at the moment, what I'm indicating it's periodic, so it's like an angle, but I don't want to label it as phi, because if you label it as phi, it comes along with a prejudice that the periodicity is 2 pi. And at the moment, I don't want to sort of slip into any bad habits, right? So by calling it psi, I'm emphasizing that, I've chosen something that looks like an angle, but because it's not phi, it just reminds you that not to treat this as if it were a standard polar, spherical polar angle. So let me just sketch this function g, or f, whichever way. So this is my function, the metric function, and typically it'll have 3 roots. if the GMA parameter is not too big. So this is 1, this is -1, and I'm sort of imagining GMA as small in this plot. So I'm going to label my zeros x1, x2, and x3. And the notion of psi being an angle suggests that we take x in x2, x3, so that we have a finite range. Now, if GMA was 0, g of x would be 1 minus x squared. If I replace x with cos theta, then I would have sine squared theta d psi squared and d theta squared. So I'd have something that looked like the metric on a two-sphere. And as GMA goes to 0, x2 and x3 move off to -1 and +1. So you can see this is sort of the flat, or a flat space limit. So that gives us, sort of deals with the range of our x coordinate. Now for y, f tending to 0 looks like a horizon. And so f is sort of minus g of minus x. So we're going to take our y coordinate to be in that range. And so if we try just doing a transformation, taking y as 1 over AR, then f now actually looks much more familiar. So we've seen that potential before. We've seen it in the context of Schwarzschild de Sitter. So our metric, if we do this coordinate transformation, so we kind of feel that this is actually looking like a black hole because we've got R is roughly 2 GM, we've got an event horizon, a black hole type of event horizon, and if R is roughly 1 over A, we've got something which is a sort of cosmological, or like Rindler, an acceleration horizon. So if we set m goes to 0, we actually get a Rindler space in spherical coordinates. So, kind of running out of time a bit here, but just to discuss what happens in terms of the x coordinate, by analogy with, the sort of GMA equals 0 limit, we want to associate x with our angle on a two-sphere. So we'd like to interpret the x psi direction as a sort of deformed two-sphere. And so what we should do then is look at the poles, which is where x goes to x2 or x3. So this is again familiar from that Euclidean argument. I'm going to let d theta squared at each pole putting small g, sorry. So I'm simply going to define a local angle, and then my g function looks like sine squared theta. But now we see why, or you're seeing why I labeled this psi. So I need to choose the periodicity of my psi angle in order that the pole is non-singular. But I can't do that unless GMA is 0. I can't do it at both poles. And so what I end up with is a conical singularity at one pole and so the picture is something like this, of a black hole being pulled. This is sort of a conical singularity, which also we sometimes call a cosmic string. And so we get this picture of the black hole being pulled by one of these conical deficits. So I realize this is kind of going through quite fast, but I'm just trying to get an image or an impression of what this metric is. And this is the C metric. It's like Rindler. It covers a quarter of the space, but we have this, it's not quite a causal diagram because, of course, this tube that I'm drawing is the event horizon of a black hole, but this is one of these pictorial diagrams. But we have, this covers one patch of space, but the sort of full analytically continued space-time has a mirror image. So you've seen that kind of with Schwarzschild. So you can actually, by using conical deficits, you can build up multi-black hole solutions. You can have black holes suspended in equilibrium by these strings. You can put these conical deficits through black holes. And so actually, there's, the set of solutions to Einstein's equations with event horizons and with other physical objects is, there's actually more you can do than first meets the eye. Okay, that's a long one.